Well, it looks to be that time of the semester where people in Calculus 2 are starting to do or finishing their interaction with infinite series, power series, and things like that. I was working with somebody the other day on some ratio test problems, and I thought, yeah, there's going to be plenty of people out there working on ratio test problems, so let's give it a run through just for a reference that might be helpful to people. So the ratio test is a test we use for assessing the convergence of an infinite series. The generic template for an infinite series is a sum of a recipe for that series, which we denote A sub n. The ratio test says we're going to build this diagnostic value, which is going to tell us about convergence or divergence of the series. We take the ratio of A sub n plus 1 over A sub n. What does that mean? It means you go grab whatever recipe is in the series for the individual terms. So wherever you see an n, you plonk in an n plus 1 instead. That's the numerator, A sub n plus 1. And then you divide by the actual series recipe itself, A sub n. Throw some absolute value bars on there so that any negative signs don't get in the way, and then run the limit as n goes to infinity. What this is doing is it's measuring whether or not the size of the subsequent terms as we get further out into the series are shrinking fast enough to get convergence. So A sub n is any term in the series that we've stopped at. A sub n is the next subsequent term in the series. So A sub n plus 1 over A sub n measures like A sub 101 over A 100. We're at a spot in the series, and we make sure that the next subsequent term is smaller, and that as we go farther and farther out in the series, as n goes to infinity, that trend is locked in. Okay, so we build our quotient, we simplify the quotient, we run the limit as n goes to infinity, and if L is less than 1, that means that as we go farther out in the series, the trend is that any subsequent term is definitely less than the term that came before it. So we're putting the brakes on, and the series will converge. If L is bigger than 1, that means the trend out at the long end of the series is for subsequent terms to actually be bigger than the previous term. So that's going to be divergence. If L is 1, you didn't learn anything. You just spent a lot of time for nothing other than practice with simplifying things. Now, when do you use the ratio test? Well, the obvious one is if you're in the section that's about the ratio test, because the instructions are going to say use the ratio test to determine whether the series converges or diverges. Now, if you're in a more broad setting where it's just here's a series, figure it out, then look for factorials. If there are factorials in the series recipe, the ratio test is a good candidate. If there are individual items in the series recipe that are raised to a power n, or maybe n plus 1 or n minus 1 or things like that, that might be a sign that the ratio test is useful. If the entire series term is as a whole raised to the nth power, then you might want to consider the root test. That's a whole other thing. The key to successful execution of the ratio test is be patient. There's a lot of details, and until you get super good at it, don't try to rush it. Don't try to get to the limit right away. Just build the thing you got to build. Simplify the thing. Not until you're done simplifying and you're happy with it, then worry about the limit value. Okay, don't try to leapfrog. Just be patient. So as a simple first example, let's take a look at this series 10 to the n over n factorial. So step number 1 is to build A sub n plus 1. That means grab my 10 to the n over n factorial and just plonk in n plus 1 wherever there were n's. So now we're going to build this ratio that measures the relative size of a subsequent term to the previous term. Since the series recipe is a quotient, this is a quotient of quotients, and so what we'll generally do is multiply by the reciprocal of the denominator, the whole invert and multiply business. So here are our two building blocks to this quotient, A sub n plus 1 and A sub n. I'm going to build the ratio by writing down A sub n plus 1 and then inverting and multiplying by A sub n upside down, which will become n factorial over 10 to the n, right? Now, as you get experience with this, here's something that you can definitely avoid and just use your eyeballs. But as you're learning, I will definitely recommend this. And that's to group things together that look alike, because it helps a lot with your simplification to see what's going on. So everything in this blob is multiplication or division. So what I'm doing is I'm moving my 10 to the n over there underneath the 10 to the n plus 1 and trading its place with the n plus 1 factorial. Because now I can take a look at this clump, take a look at this clump, and I can really see the simplification that's going to happen, right? This 1 on the left cancels to 10. This 1 on the right becomes 1 over n plus 1. Now, footnote, I'm assuming that you're okay with factorials here, because that's a whole other thing. But n factorial divided by n plus 1 factorial is n factorial divided by n factorial times n plus 1. So the n factorials cancel. Okay, and so now we've built this ratio. We're going to run the limit as n goes to infinity, and that's pretty obviously 0. And the limit that we found, the diagnostic value, is less than 1, so the series converges. Okay, so here comes a second example that's going to be more complicated. But again, the advice is just be patient and don't rush things. So we got -1 to the n times n factorial over the quotient n over e all to the nth in the denominator. Okay, so I'm going to build a sub n plus 1. Yuck. All the n's have been replaced by n plus 1. It is what it is. Here are a sub n and a sub n plus 1 side by side, so that we can now build the ratio a sub n plus 1 over a sub n. And again, remember, I've just put a sub n plus 1 down and then inverted and multiplied by the a sub n recipe. All right, now I'm going to start pushing things around left to right to group things together that look like they go together, such as the powers of -1, the factorials, and all the other junk with the e's. Okay, and again, it's all just multiplication, so I am allowed to reorder my multiplication and my division as long as I do it correctly. Now, we can see what sort of simplification might be taking place. I've, first of all, stripped, well, this quotient of powers of -1 is just -1, but we're inside absolute values. So at this point, just bye-bye to the -1s. And now we can drop the absolute values because everything else is strictly positive. Okay, now I'm going to clean this up a bit by doing another round of invert and multiply. So this n over e all raised to the n in the numerator, I've written out explicitly, and then I've taken what was the denominator and inverted and multiplied to get things all in a nice row and no more quotients within quotients. This is all just top level, bottom level. And then I'm going to group my things. My powers of e are now together and all the leftovers are together. Again, when you're good at this, you don't need to do that. You can just probably see directly that you've got an e to the n plus 1 in the numerator and an e to the n in the denominator. So just let it go. But patience and detail, I want to make sure to show those groupings so that you can emulate this when you're first learning these things. All right, simplifying. The ratio of factorials just becomes n plus 1. The ratio of powers of e just becomes e. This thing on the right, what the heck? Okay, but so we can't do much with it, but look at what happens here at least. There's an n plus 1 from the leftovers of the factorial terms, and that denominator on the other side are powers of n plus 1. So we can just cancel one instance of n plus 1. And now we're left with this. Now we want the limit of this expression as n goes to infinity eventually. Well, at least I can, pull off a power of n and write it as the fraction all raised to the n by itself. But then I've got to consider the limit. At least for this limit, e is a constant, so I can factor it out. But what the heck? What is this thing? You might think it's 1. You can't see that sentence because I dropped my mouse too far down and the editing bar popped up. So now it's gone. Okay, now down here in this quotient, n over n plus 1 by itself, as n goes to infinity, that goes to 1. So and since 1 to any power is 1, this limit ought to be 1, right? That's not how it works. This is an indeterminate form. There's a fight going on between what's inside the parentheses and the exponent that's on the parentheses. So sure, the n over n plus 1 is trending towards 1, but the exponent of that whole thing is trending to infinity. Which one wins? Right? That's why you don't quite know whether or not this thing balances out at 1. Now, we've put this current version of the limit on hold, and I'm going to present to you this limit, which you should learn to recognize, because you're going to come across limit expressions like this that can be related to this limit, such as the one we're in the middle of working on. Okay, but just learn to recognize this one. The limit as n goes to infinity of 1 plus 1 over n to the n is e. So again, the internal part, 1 plus 1 over n, certainly is heading towards 1 as n goes to infinity, but it's being pulled in the other direction because the whole thing is being raised to an exponent, which itself is going to infinity. So which trend wins? The trend for the inside part to go to 1, or the trend for the outside bulk to be raised to a power going to infinity? And it turns out that this balances out at e. Now, what does that have to do with the limit we're working on? Well, watch this. N over n plus 1, which is what we are working on, is the reciprocal of n plus 1 over n. N plus 1 over n can be expanded out to 1 plus 1 over n. Okay, so n over n plus 1, like we have in our limit expression, raised to the n, is the same thing as the reciprocal of 1 plus 1 over n raised to the n. With those two powers, I can reverse them so that now I've got the reciprocal of 1 plus 1 over n to the n, and now looky there. So the limit that we're working on is actually this standard limit in disguise, right? So we are working on this limit to discover our diagnostic value of the ratio test. We now figured out that that's the limit of the reciprocal of this magic 1 plus 1 over n all to the n. The limit of that reciprocal is the reciprocal of the limit. That's limit stuff about when you can and can't distribute limits across operations. But we're going to go with it here. And this limit in the square brackets is the one that you should be learning to recognize is e. So this limit boils down to e times e to the minus 1, which is 1. So our diagnostic value for the ratio test for this problem turns out to be 1. And that is the case where we have done all this work and we have learned nothing, except that the ratio test tells us nothing about the convergence of this series. Now, how do we actually determine the convergence of the series? I don't know. But not by the ratio test, that's for sure. Okay, for those of you that are moving on into power series, here's an example where the ratio test can be used here. If you haven't done power series, then thanks for watching, see you later, or just hang out and watch, and then you'll be prepared for the problems that you are going to encounter. Ha ha ha. So we are going to determine the interval of convergence for this power series. Like I was saying towards the beginning, hey, there's a factorial, and hey, there's individual items in our series recipe being raised to the nth power. So the ratio test might be a really good idea to use to assess the convergence of this power series. Now, remember that this power series has x's in it. That's the difference between this thing and the things we were working on before, which means that it's a different series for every value of x that we can plug in. And there might be values of x that we can plug in to produce a series that converges. There might be values of x that we could plug in that would produce a series that diverges. What's the bucket of values of x that will allow for convergence of this series? That's the interval of convergence. Now, since we're super good at this now, I'm going to speed up my process of building and arranging the quotient of a sub n plus 1 over a sub n. So I've taken the series recipe and I've plonked in n plus 1 in place of n's right there. And now I've taken the original form for the recipe a sub n, inverted and multiplied. Here I'm grouping, my powers of 10, my powers of x, and my factorials. Here I have exactly the same line as before. I must have cut and pasted one too many times when I was building these slides. The powers of 10 simplify to 10. The powers of x simplify to absolute x, and then the factorial ratio turns into 1 over n plus 1. And also what I've passed through the absolute values, because the powers of 10 are always positive. The ratio of the factorials is always positive. The business with the x's might be positive, might be negative, depending on the value of x. So we can factor everything out of the absolute values except for the batch of stuff with x's and its simplified version. So that's the ratio a sub n plus 1 over a sub n within the absolute values. So now we ask, what's the diagnostic value L? Well, we take this 10 absolute x over n plus 1, ask for the limit as this thing goes to infinity. And, x could be really, 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 really big, but it would still be a constant. And so the limit as n goes to infinity of the numerator, which for any one x value is a constant, divided by a denominator which is going to infinity, that's always 0. And so that means that this series converges for every x. There is no value of x we could plug in that would lead to divergence. And that means the interval of convergence is the entire real number line from minus infinity to infinity. There's also a thing called the radius of convergence, which is half of the length of the interval of convergence. And so in this case, that's also infinity. The term radius of convergence can throw people off in Calc 2 because you're talking about a number line. What the heck is a radius on a number line? This is a inherited term from the study of complex variables where the numbers themselves are displayed in a plane. And so the set of numbers that might lead to convergence, if we're allowing complex numbers, could actually come from a circle in the complex plane. And so the idea of a radius of convergence makes more sense there. While we go down just to the real number line, we inherit that terminology and call it a radius, even though it's just, here's your interval, let's take half the interval. It's still called the radius of convergence. Okay, so that all that work, and it wasn't a very exciting power series because it turns out that it converges no matter what x is. So here's an updated version of it. Now this time I'm just going to zip through the limit calculation, building the diagnostic quotient, running the limit as n goes to infinity. So if you want to pause and practice on this one and make sure you come back with the same thing, then please do. But when I build a sub n plus 1 over a sub n for this new series, simplify things, run the limit as n goes to infinity, I've got a ratio of n over n plus 1. That's going to go to 1. And so it all shakes out to be absolute x over 10. Okay. Now, what do we do with this diagnostic value? We decide when it's going to be less than 1. That will signal convergence. So we need absolute x over 10 to be less than 1. That means we need absolute x to be less than 10, and that means we're in the stretch of the real number line from minus 10 to 10. That's where we find values of x that we can plug into this series and get a series that converges. Or is this the interval of convergence? Haha. There's a subtle extra bit here, which I will call the great killer of points. I have taken more points off of test problems on the ratio test for people forgetting to do this than any other error that gets made during the ratio test. So any test problem about use the ratio test to determine the interval of convergence of this power series, 10-point problem, the number of times I've ended up having to give a 7 because people forgot to do this extra bit, it pains me to think about that. But here's the story. The diagnostic value for the ratio test, this thing we called L less than 1 signals convergence. And we found out that this L is going to be less than 1 whenever x is between minus 10 and 10. Okay, that's fine. When L is greater than 1, we're going to get divergence. So everything outside of this interval from minus 10 to 10. That's the collection of x values that will lead to divergence of this series. But remember that third thing that already got us back on a previous problem here. If L is equal to 1, the ratio test is inconclusive. So sure, the interval of convergence is built as negative 10 to 10 because that's where L is less than 1. And outside that interval, we get divergence. But what about right there at the points where L would actually be equal to 1? Well, where are those points? Those points are the endpoints of the interval. And so having used the ratio test to assess and find an interval of convergence for this power series, we aren't quite done. We still have to go back and test the endpoints individually to see if we get convergence at those endpoints. So check the damn endpoints. Don't lose points on a test because you forgot to do this. Even if you try it and don't do it right, that's better than forgetting it altogether. Okay, so our current interval of convergence starts at negative 10 and ends at 10. But what happens at negative 10 and 10? Well, at x equals negative 10, imagine plugging negative 10 in for x in this series. There's negative 1 to the n times negative 10 to the n. That negative 10 to the n cancels with the 10 to the n underneath, just to leave negative 1 to the n. So all the negatives are gone. There's a couple of different ways through that simplification, but the fact is the fight between the negative signs and the tens shakes out to leave us a series of 1 over n. That is the harmonic series, and we already know that it diverges. So when we plug in x equals negative 10, we will get a divergent series out of this. But when we go to x equals positive 10, the powers of 10 cancel immediately. And now we're left with the sum of negative 1 to the n over n. This is the alternating harmonic series, and it converges. Okay, so we have this stretch of the number line from minus 10 to 10. Everything inside that interval provides convergence for this series. At the endpoints, when we use one endpoint, we get convergence. When we use the other endpoint, we get divergence. And so, there's that recording bar again. Go away. There. So what used to be the interval from minus 10 to 10 with rounded indicators for that interval, we actually have discovered that at 10, we want inclusion because 10 itself will lead to convergence. And so we use a square bracket on our interval at the 10 to indicate that number is included in the series. Okay, or we could write negative 10 is less than x is less than or equal to 10 if you like writing your intervals that way as well. Okay, so don't forget that endpoint, of a ratio test problem when you're using it to analyze intervals of convergence for power series. Okay, so that's been more than 20 minutes on the ratio test. 4 examples all the way through from simple to intermediate to power series and checking the damn endpoints. Don't forget that.